Thank you for everyone for joining today's talk, and as part of distinguished webinar series in AI and cybersecurity. This series is hosted jointly by School of Electrical Engineering and Computer Science and Centers for Artificial Intelligence and Cybersecurity at the UND. And we also have a number of other institutions also co-sponsoring or agreed to help us in promoting this event. So thank you, those participants as well. And today's talk is actually titled Overparameterization Improves Robustness to Covariate Shift in High Dimensions, featuring Dr. Ben Adlam. And Ben is a research scientist at Google Brain, working to understand deep learning and apply to basic science problem. He joined Google in 2018 as an AI resident, and before he was a PhD student in applied math at Harvard, where he used techniques from probability theory and stochastic process to study evolutionary dynamics and random matrices. Ben, thank you so much for agreeing to this talk. We are so grateful for your time today. I appreciate for sharing what you have to share today. So we're excited for this event, and the floor is yours. You should be able to share your screen.
Great. Yeah, thank you for that very kind introduction and the invitation to speak to everyone today. I'm just going to present my screen, and maybe you can tell me if it's showing up on your end. Is that okay?
Looks good. Thank you.
Great. Okay. So today I'm going to talk about some theoretical work that I did with Nilesh and Jeffrey, who are also research scientists at Google Brain. And I hope this notion of robustness for machine learning models is relevant to the people attending the seminar. I'm sort of happy to take clarifying questions as we go through the talk. So I'll try and keep an eye on the chat and things like that. But yeah, happy to do that, or wait till the end to take more questions. And I want to start with some sort of general motivation for this talk and a lot of the work that I've ended up doing at Google over the past 4 years. And I like this plot a lot. So let me just describe to you what it's showing. So here you can see data from different papers in machine learning going back to the 60s. And these papers were selected for being notable in some way. So perhaps they got a lot of citations or achieved state-of-the-art results on an important benchmark. But you can take a collection of papers like that and then filter down to those papers that report both a parameter count for the models that they use and a training data set size for the amount of training data or the number of examples that those models were trained on. And you can make a scatter plot. So each point here represents a single paper or a model. And what you see on this log-log scale is a very strong trend that goes back many decades of scaling up both the models that we use and the amount of data that we use to train those models. And people have been very deliberate about this recently in deep learning, where we have seen lots of active progress in trying to scale up models and make the sort of largest neural networks ever, and then also handle text corpuses with trillions of tokens, for example. And I want to kind of situate that recent trend in this larger trend that's been going on for a long time of scaling up these two quantities simultaneously. And you can see that there is a more or less linear relationship between these two things. And what's interesting from my perspective here is that this is quite different than the classical statistical learning theory point of view. So I think of that classical theory as sort of justifying why machine learning works. And when I was when I was an undergrad and in grad school, this is like how I learned to think about machine learning. And there you're often thinking about fixing a model class and then taking the amount of training data that you have to become large, or taking that limit and looking at the asymptotics when you have lots of training data. And here that would represent the top left corner of this plot. But what you can see is that the state-of-the-art models don't live in this regime. The state-of-the-art models live in this high-dimensional regime where we have lots of training data and very large models with lots of capacity. So the theoretical work that I've done is try to look in this high-dimensional limit. And one way to sort of ask this question now more precisely is to say, there are lots of things that we've discovered empirically about neural networks and deep learning that seem surprising or interesting. And of those phenomena, which are truly properties of neural networks and which are due simply to high dimensional statistics, to being in this different regime. So, what we want to do is kind of build a null model, a simple model that is high dimensional, but doesn't have all the complexity of deep learning, and see if we can replicate these phenomena. And if that's possible, it really tells us that we're observing something that is a high dimensional effect rather than something particular to neural networks. And to give like a little more motivation, here's an interesting set of data. So imagine that you ran an experiment like this and you are wondering, have I discovered anything interesting? Was there, something in this experiment that I can now write a paper about, for example? And obviously the answer to that depends on what you expected to see when you ran the experiment. If you expected an upward trend, then this downward trend might be very surprising to you. However, if you expected a downward trend, the data are less surprising. But it really depends on how well you know your prior expectations, to what degree of accuracy you thought you could predict the experiment. So we could imagine we have an even better fit for our data, and we can see now most of the points seem to lie very close to the line. However, there's a small blip here, and the question is like, is this a discovery, right? And it turns out in this case, this was a very important discovery. These data are actually from CERN, and this is the evidence for the existence of the Higgs boson. And we can sort of look at that background model, that null model for what we expected, and subtract that away from the experimental data. And now that small blip actually becomes a 5 sigma deviation from the null. So it represents good evidence for this discovery. And I think that's what we should be trying to do with deep learning, is develop these very sophisticated models for what we expect in our experiments with deep learning. And I hope this justifies like the importance of doing that to a high degree of accuracy. So with that null model, what kind of things could we look at? And here are some candidate phenomena that we could consider for things that are particular to deep learning and special about deep learning, and phenomena that have surprised people empirically. And I'll go through these. I'll focus in this talk mainly on the last two, but I think it's important just to give some context for the other ones. So the first phenomenon is this idea that overparameterized models are actually optimal in some sense. Like, not only do they generalize well, but it's also the best thing to do. And this idea is called benign overfitting. And again, the reason this is surprising is because it contradicts that classical theory that I mentioned at the beginning of the talk, right? So there, the classical theory would say these models should not generalize, and they would expect them to have a very large test error, definitely not to be the optimal modeling choice. Benign overfitting suggests that that's not the case. So it's something that needs to be explained. A kind of more refined version of this benign overfitting picture is called double descent. And that is the idea that you have a classical bias variance trade-off regime that we know about from sort of like long-standing theory. And then after that, once we go through the interpolation threshold, which is the point where our models can exactly fit our training data, we see a decrease in the test loss and a decrease in variance. And we actually often find optimal behavior in that overparameterized regime. So what is causing that behavior? It seems like it's something that comes up a lot when you're training neural networks. Can we describe that and explain the real cause of that? And then for this talk, I'll focus more on these last two, as I mentioned. This is the idea that not only are overparameterized models good when your test data have the same distribution as your training data, but they're also more robust. So if our training data are from a different distribution than our test data, it's still better to use overparameterized models. And here you can see a snippet from a 2020 paper where the authors explicitly recommend using larger models to increase the robustness of machine learning systems, in particular to distribution shift. That's the kind of robustness that I mean here. And a kind of more refined version of this view is the following. So this plot here, I'll just explain briefly. It's from a Recht et al. Paper. And here, the authors looked at several different ImageNet models. So they were trained in different ways. They had different architectures. And they took those models and evaluated them on the original ImageNet test set and then on various different test sets. Some of those were supposed to have the same distribution, and others were deliberately of a different distribution. And what they found is that making a scatter plot of those two test errors, you can see a very strong linear trend between these two quantities. And again, there's no explanation for that behavior from the classical theory point of view. So yeah, this is something that we want to try and explain. And the null model that I'm going to suggest in this talk for deep learning is random feature regression. So random features, I'll say mathematically what they are in a short while, but you can think of those as a neural network where you initialize the neural network with all its parameters randomly. And then rather than training all of those parameters, you only train the parameters in the last layer of the network. So it's quite a simple model. And it has some of the architectural complications of deep learning models, but is a lot simpler in other ways. So what are the advantages of studying random features? Well, the first is the simplicity buys you a lot in terms of what you can analyze theoretically, and we'll see that today. That's the core reason. But they also replicate a lot of the important properties of deep learning systems. And the main one for us will be that they can also be high dimensional. So they can handle data that are high dimensional, and they can also have a large number of parameters relative to the size of the training set. So that's going to be important for us to probe that high dimensional regime that I showed in the first plot. Another advantage that they have over linear regression in particular is that they decouple the model complexity from the data. So for linear regression, the number of parameters that you have is fixed by the data dimension. There's no way to change that. But in random feature regression, I can fix my training data and probe this whole regime of under and over parameterized models. And if you want to study something like double descent, where you're explicitly looking at this transition based on the number of parameters that you have, this is a really core property for the kind of models that you want to use. Another advantage is that they're randomized. So just in the same way, if you take a neural network and you change your random seeds and rerun the training process, the ultimate predictive function that comes out of that training process will not be the same. It will have dependence on the random seed that you used. And that's true for random features too. Even conditional on the training data. So you don't have to think about resampling the training data. That's not the case, again, for something like linear regression. And then finally, I kind of mentioned this at the beginning, but they have these connections to neural networks, which are important. So, the main one here is that you can think of it as a neural network where you're only training the parameters in the last layer, but there are also more sort of like sophisticated connections, particularly via this object called the neural tangent kernel, which maybe people have heard of. I won't talk more about that today, but you can kind of think of that as a highly structured random feature method. Of course, they have disadvantages too. So the random features are much simpler than neural networks, and in that simplification, you lose some features. So if you wanted to study something like feature learning, obviously random features are a bad way to do that, right? So the features are chosen randomly. They have no dependence on the data. So while we all believe that feature learning is important in neural networks, random features are clearly not the model to study that. Second problem is that the optimization problem for random features is convex. So it's a very simple optimization problem, and that loses some of the complexity. People are pretty convinced that the non-convexity in the optimization could have important effects on the models that we see. So again, random features are not the model to study kind of optimization questions. And then finally, while you have this link to neural networks, very complicated neural network architectures generating random features can still be difficult to analyze, right? So more complicated architectures like recurrent neural networks or transformers can still be tough to study despite the simplifications that random features bring. And in this talk, we're going to focus on the simplest model of random features. So a neural network architecture that is a single hidden layer, fully connected neural network, basically, and the random features that generates. So now let me define distribution shift and say a little bit more about that and the particular case of covariate shift. So distribution shift is not the exception, basically. If you do anything in practice, distribution shift is the norm. So, and all it means is that the distribution your training data was sampled from is different from the one that you see when your model is deployed, or what it encounters at test time. So obviously you have these two distributions, the training distribution and the test distribution, and there's only one way for those to be the same, but there are infinitely many ways for it to be different. So distribution shift is actually not saying very much in and of itself. There are many different types of shift, and it's important to sort of concentrate on particular kinds. And in this talk, I'll focus on covariate shift, and I'll define that precisely in a minute. The image here is from a video, which I encourage you to look up because it's quite fun. But here you can see the Tesla autopilot system mistaking the moon, which is very yellow on this night for some reason, as a yellow traffic light. So you could argue that distribution shift is actually a good way to view what is happening in this video, right? So the training distribution did not have any support on the example where the moon was this yellow. And the AI system now is behaving in an unpredictable way because it's being tested on data that's quite different than it saw during training. Okay, I want to say something briefly as well about ways you could approach the distribution shift problem. In particular, how you would do that from a classical statistical learning theory point of view. So the natural approach there would be to say, what if my training and test distributions are not too different? And not too different can be formalized as, for example, saying that some divergence between those two distributions is not very large, right? So that's violating the IID assumption, which is really common in all of statistical learning theory, more or less. The IID assumption, I mean that by the IID assumption, I mean that the test points are sampled from the same distribution independently as the training points. So we could relax that assumption with this divergence bound. And while those that IID assumption is important, it doesn't assume much else about the training distribution, other than some like ruling out some pathological behavior. It's basically a distribution-free result, typically in statistical learning theory, where you are just really relying on the independence. And that's good because it means that we don't have assumptions that we have to check in practice for our theory to be valid. It has a wide applicability. We don't need to verify some like esoteric property of the distribution to have our theory be valid. But the problem is, to have a bound that works for all distributions is fundamentally a worst case bound. It's saying that you can guarantee this behavior no matter what the distribution. And the problem then is that the theory you get out is not very descriptive of what you see in practice, right? So if you run experiments empirically, the bounds that you get are often very loose or uninformative. And that gets even worse under distribution shift because now you're adding another worst case scenario of, how bad can this shift be given this bound on the divergence? And the kind of bounds that you get out from this analysis just do not describe the deep learning regime that we're interested in. So instead, I want to kind of suggest a different approach in this high dimensional limit. And that's instead to look at average or typical performance rather than worst case performance. And the downside of that is we need to make specific assumptions about our data generating process. So the results will not be distribution free in the same way. And the tool set that we'll use to do the analysis is quite different. So here we used random matrix theory, which is kind of a natural a toolbox from probability theory to apply to this problem. But the most important thing is that it will be more descriptive of the empirical results that we're seeing. And I'll be more specific in a second about exactly how that shift works. So what is covariate shift first? I told you that there are lots of different types of distribution shift. So let me be precise about covariate shift. So you can imagine that you're doing a supervised learning problem where you have inputs X and labels associated to those inputs Y. The covariates are just the inputs. So here we're assuming that the distribution, the marginal distribution over the inputs will change between the training and test distributions. But the conditional distribution of the labels, given the covariates, will remain the same. And that's kind of a natural assumption because in supervised learning, you could just view that as trying to learn this conditional distribution, right? So we'll assume that the target of learning hasn't changed between training and test, but kind of the way we're evaluating how well we've learned that conditional distribution will change. And to be very specific about this, the data generating process that we study is the following. So we consider n0 dimensional training data that are multivariate Gaussian. We assume the mean is 0, mainly for sort of simplicity purposes. You could imagine doing the analysis with a non-zero mean. But the core thing here is that we have some covariance structure. So we have a covariance matrix sigma that is describing the correlations in the covariances, or in the covariates, sorry. And then we label all of the inputs with a linear function beta, and we add IID label noise to all of the points. And this is basically just describing the joint distribution between X and Y in this problem. The linear labeling function seems like it might seem like it's restrictive. It turns out in high dimensions it's not, but that's kind of for a more complicated technical reason that I won't get into. Okay, so where does the high dimensionality start to come into this? Well, we imagine that we form a training set from that joint distribution. So we sample m different points from the joint distribution, and we'll assume that the dimensionality of the data, n0, and the number of samples are both large and comparably large. So if we look at their ratio, that's roughly this constant phi. You know, more technically here, we're looking in the asymptotic limit where both these dimensions diverge to infinity and their ratio is held at this fixed constant. But you know, if you run a simulation for say a few hundred for these system sizes, you know, the theory that you get asymptotically will be very descriptive of those finite simulations. So you can just think about those as being large and large kind of simultaneously. And okay, now for the covariate shift part, we test on a point which is sampled from a multivariate Gaussian, but with a different covariance structure. So rather than having covariance sigma, it has covariance sigma star. Okay, so then the random feature model that we try to learn this data with is given by the following. So it's, again, think of this as a single hidden layer fully connected neural network where we're only learning the last layer. We sample the weight matrix, the hidden weight, IID Gaussian. That's like a typical thing that you do in practice. And then we generate the random features for an input X by multiplying by that weight matrix and then coordinate-wise applying an activation function. So this gives us, and there's some normalization here too. This gives us N1 random features. And then for each of those random features, we basically do a linear regression on top of that, right? And we have N1 parameters that we will fit based on the training data. Again, we're assuming that we're in this high dimensional limit. So here, N0 divided by N1, that ratio is going to be roughly constant, and both of those quantities will be large. And here, N1 is the number of trainable parameters, right? So you can think about this equivalently as saying the number of training points and the number of trainable parameters are both large. So we're looking in that high dimensional limit that I discussed at the beginning of the talk. And then the predictive function that comes out of this from just fitting the last layer in this way that I talked about is the same as you would get from doing kernel regression with the kernel defined by these random features. And I won't go too much into this, but really the solution to that, because it's a simple convex optimization problem, can be expressed in closed form. It's just the solution of a linear system, and you have this exact expression for it. And the real key point here is that it is a rational function of the underlying random matrices in this problem. And that fact enables the whole analysis that we do. And very simply, the thing that we're trying to calculate to get theoretical predictions for is the expected test error. So what do I mean by that? I mean, we're doing a regression task. So we look at a label versus our prediction for the label, y hat, and we measure that in mean squared error. And we say, on average, how much test error do we have? And then that's describing the inner expectation. The outer expectation here is kind of a frequentist notion of rerunning the algorithm. So this is what I meant by looking at the typical performance of our algorithms. It's kind of interesting that it turns out that in high dimensions, the average behavior is the only behavior that you see. If you remove that outer expectation, you can prove some concentration results. But I'm not really going to talk more about that. You can just think about it as the average test error, basically. And this is a very complicated calculation. I would sort of refer you to the paper if you're interested in learning more about that. But I want to talk mainly just about the results. Like, given that you have these theoretical predictions, what can you learn about the test error? And yeah, we'll get there shortly. So to describe the results, I need to introduce these things called overlap coefficients. And what these are basically trying to parameterize the difference between sigma and sigma star. So in particular, Ri projects sigma star into the ith eigendirection of sigma. So you can imagine doing an eigen decomposition on sigma. That will give you some eigenvalues. And we could ask, how large is sigma star in that eigendirection? Roughly is what this is doing. So the V's are eigenvectors, the lambdas are eigenvalues, and the star will denote sigma star versus sigma. So you can see here that Ri is kind of measuring the size of sigma star in this eigendirection Vi. And when we have these collection of coefficients, so there will be n naughts of them, we can start to think about different shifts and how shifts change the test error. And to give you a very concrete example of a shift, and probably the simplest one that you can come up with, imagine that we had a covariate structure for sigma, which is independent. So all the coordinates act independently, but they have different scales. And how you would do that, if you just had two different scales, might be in this way. So we have one scale alpha and then another scale 1 over alpha. And then we set the number of directions which have scale alpha versus 1 over alpha based on a normalization condition, which just says that the average trace of sigma should be 1. And that's just a scale condition that, assuming that, makes all of the analysis much simpler. So I'll make that assumption for this talk. And then how do we shift that distribution at test time? All we do is we take sigma and raise that to a power theta, and then multiply by some normalization constant to maintain this average trace at 1 that I mentioned. So given these definitions, we can compute the overlap coefficients. And in this case, because the eigenvectors have not changed, only the eigenvalues, the overlap coefficients adjust the eigenvalues of sigma star. So you can see here that we've just raised some of those eigenvalues alpha to the power theta, and we're assuming alpha is greater than 1. And what that means is that when theta is greater than 1, the large eigendirections have increased in size and the small eigendirections have decreased in size. And when theta is less than 1, the reverse is true. And that can start to give us some intuition on how this parameter theta will affect our learning. So as a kind of warm up to the random feature regression results, you could try to calculate the expected test error for linear regression. So here, again, there's a closed form solution for the optimal predictor, beta hat, for linear regression. And you can see that we have this exact expression for the expected test error. And there are three main components to that test error. So first, you have this sigma squared epsilon term, which is just describing the noise in the labels. So you would expect, if you have more noise, that you would see a larger test error, for example. Then the second factor here is a ratio of dimensions, and that's describing how the high dimensionality of the problem affects the test error. And then finally, we have this sum, and the sum is very interesting. That is basically decomposing the test error into the individual contributions from the different eigendirections. And in the case of no shift, which is what had been studied before, you would find that Ri is equal to lambda I, just from the definition of the Rs. So this factor is 1 in that case. So when there's no shift, this exactly drops out. But we can see that when we do have some kind of covariate shift, we have a ratio. So in the denominator, we have lambda I. And the intuition for that is that lambda I is penalizing the different eigendirections based on how well you are able to learn them from the training data. So when you have very low frequency modes, that means large lambda I, those are easy to learn from the training data because you see a lot of variation in those in the training set. The reverse is also true. So if I have a high frequency mode and lambda I is very small, those are really difficult to learn from the training set. So relatively speaking, we learn those less. Now, the numerator in this expression is telling us how much the test distribution will penalize us for the different eigendirections. And that's based on this fact of like how much weight sigma star has in that eigendirection, right? So if we have a large overlap with a particular eigendirection, and that's more represented in the test set, it will be penalized more in the test error. And what's interesting from this formula is that you could start to think about making a definition for which types of covariate shift are hard to learn and which shifts are easy. So here, imagine that you have two different covariate shifts, so two different test distributions, sigma star 1 and sigma star 2. And they will have overlap coefficients associated to them. Then the key point here is a sufficient condition to say that the test error for the second shift is larger than the first, is that the ratio of their overlap coefficients form a non-increasing sequence. And that's a simple result that you can prove with the Harris inequality. It's literally like a one-line proof. But that sufficient condition is a way to motivate talking about hardness for covariate shifts. And we can turn it into a definition. So imagine that we have two shifts and that this non-increasing sequence condition holds for their overlap coefficients. Then we can say that the shift 2 is harder than shift 1. And a natural question is, this was a sufficient condition for linear regression, like does it translate for random feature regression as well? And I'll talk about that right now. So there is a lot of information on this particular slide. So I'll try to walk through it reasonably slowly, but it summarizes the main technical results in the paper. In the top row, you can see 3 different contour plots. And those are describing the total error and then the bias and variance, these different components of the test error. The x-axis is something called the overparameterization ratio. So that is describing the number of random features relative to the data set size. So when this quantity is 1, that's exactly the interpolation threshold that I mentioned before. And then the y-axis is the shift power in this diatomic shift example that I gave you. And you can think about that as the hardness of the shift. So -3 is a very hard shift, whereas +3 is a very easy shift. And this axis interpolates between hard and easy shifts, with the case of no shift being at 1. And we can see some monotonicity conditions like being satisfied in these plots. So in the second row, we plot different slices of these contour plots. So let's focus on the sub-panel D for a second. And here the x-axis is this overparameterization ratio. And what we see is that the double descent behavior translates into models under covariate shift 2. So in particular, the bias is monotonic for all shift values and all overparameterization ratios. The variance has a single peak at the interpolation threshold. So we see this explosion in variance and then this decay after the interpolation threshold once we enter the overparameterized regimes. And you can prove all this mathematically. And in many cases, the optimal test error is in the overparameterized regime. So this supports that original idea that we started with of larger models being more robust and just having lower test error. And again, this is a behavior that we're replicating in a very simple random feature model, right? So it's not something that's particular to neural networks. In the panel E, the x-axis now is the shift power, and you can think about that roughly as the hardness of the shift going from hard to easy. And we can see for this particular example, all of these quantities are decreasing monotonically with the hardness of the shift. It turns out that the bias is always monotonic in this shift power, but the variance can actually be non-monotonic. And it can be so non-monotonic that it causes the total test error to be non-monotonic. So without an additional condition, which is to do with the size of the label noise, actually, without a bound on the size of the label noise, the hardness definition of shifts can violate this test error ordering, basically. But it is always true for the bias. And then finally, in the panel E, we can see something called the generalization ratio, or generalization gap, sorry. So what this is the test error on the in-distribution data versus out-of-distribution data, and it looks at the size of the gap between those two things. And in this example, we can see that it's always positive, so the shifted test error is larger. But what's interesting is that this gap is actually a decreasing function of the overparameterization ratio once we're past the interpolation threshold. So again, it's supporting that idea that larger models are more robust. And again, this is like a theorem in the paper that we were able to prove. And then finally, I want to talk about these linear trends that I mentioned at the beginning. And here you can see a different set of data from the Recht et al. Paper. And it looks at lots of different models, as I said, for ImageNet, and it evaluates them on in-distribution test data versus some shifted test data. And here there are two different examples of a shifted test set. The first is something called ImageNet V2 Gray, which contains grayscale images rather than color images. So you can imagine that this would be a hard shift for the classifiers to deal with because you're losing a lot of information. And that is indeed the case. So we see worse performance on ImageNet V2 Gray than the original ImageNet test set. That's why it's below this dashed line in the plot on the right-hand side. And the second test distribution is called ImageNet V2 Top Images. And roughly, these are the easy images in the test set. And you can see that the performance on that easy test distribution is above that line, right? So we have this idea intuitively of a hard and an easy shift. And we find that there's a linear behavior between the accuracies, as I mentioned. But more than that, if you look at the coefficient for the slope of these two lines, the hard shift has a slope greater than 1 and the easy shift has a slope less than 1. And for us, this was behavior that we could replicate exactly in this random feature model. So you can see on the left-hand side, sorry, the results that we get from our theoretical predictions for a similar task. And we find conditions for the linear behavior. Overparameterization is very important, it turns out. And a lack of substantial regularization is also very important. And given those two things, you can see linear trends in the different test errors. And we also predict this behavior with the slope being less or greater than 1, depending on whether the shift is hard or easy based on our definition. So I think I will wrap up here and just pause for some questions. But to conclude, I think that the 4 points that I mentioned earlier are actually effects of high dimensionality. They're not really effects of deep learning. And having a good null model for that allows us to really separate the sort of important phenomena for neural networks versus these other high dimensional effects. So thank you very much for your attention, and I'd be happy to take some questions.
Great. Thank you so much, Ben, for an interesting talk. And it's very interesting to see how these overlapping coefficient that you're measuring through the eigenvalues has the impact on this covariant shift. So I'm just learning as you present this, maybe while we wait for questions, and maybe I should start with some questions, what is this size of random feature that you're talking about? You said you choose a feature set in a point X and you focus on populating these sigma 1 or an N1 and sigma 1 and sigma 2. Could you talk more about, in specific to, this is very high dimension data set. You're talking about very large data sets, right? So I think, and does this particular covariant shift only applies to high dimensional data set, which means what is high dimensional? You showed me that 10 power scale. I'm just curious to see, does it not apply to small scale data sets?
Yeah, great question. So you can derive similar results for low dimensional data. And by similar results, I mean just sort of predicting what the test error will be in that case. The problem is that you won't see a lot of the phenomena that I mentioned here. So in particular, like this explosion of variance just is not possible to model that, as far as I know, without these high dimensional systems. One thing that's kind of interesting, if we want to touch more on practical things you can do with these results, is that here I'm sort of, even the overlap coefficients are defined based on the population covariance matrices, right? So they're properties of the distribution that for a real data set you wouldn't know, and it's also not easy to estimate them from real data because of these high dimensional effects. You're basically undersampled to do that. So one thing that we tried to do in this project, which we weren't successful with, was kind of take real data sets, estimate these population covariance matrices, and then calculate whether a shift was hard or easy, right, for a real data set. And so there are real issues there of just like actually verifying these assumptions about the distribution. This is kind of what I was talking about. So making the results practical in that way is quite challenging, and we weren't able to do it. So when I talk about hard versus easy shifts in this final example here, I'm speaking more intuitively, right? So I'm saying that gray seems like a hard shift and top images seems easy, but I don't have a way to sort of connect that with the theory. So this is like talking about the advantages and disadvantages of doing this kind of analysis, right? So for the real data sets, it's difficult to connect the assumptions to them, right? However, the theory that you get is kind of more descriptive of what you see in practice. So there's this constant trade-off between that type of analysis. And in low dimensions, you could do what you're saying. So you could accurately estimate the population covariance matrices and really like check these conditions. But you would lose some of the behavior that we're trying to model. So there's this kind of trade-off between the two things.
We have a question. It says, how does transfer learning relate to covariance shift?
Yeah, that's a good question. So I mean, my answer is I don't know yet. But we have thought about trying to adapt this model to the case of transfer learning, right? There things are maybe slightly different, right? So you could imagine that what you're really learning about are the covariates, and the way that the covariates are kind of used in different tasks is to have different conditional distributions. So in some ways, it's like the opposite of covariate shift, right? And the other weakness here for transfer learning and trying to study that with random features is that you need to make some modification, because usually what people talk about with transfer learning is learning the features, basically, right? So I think there are like very toy models that you could pull out of this that might say something about transfer learning, but nothing that is like close enough to really like warrant doing the calculations. But I think it's an interesting question, and I would be excited if someone could, really connect this work to that.
The next question is, can GANs be used for generating data to overcome this issue?
That's a great question. So it depends what you mean. So I think one of the weaknesses of this kind of analysis is that the data distribution we're talking about is pretty trivial, right? It's a multivariate Gaussian, and that's an advantage in the sense that it's very simple and you can do the theoretical calculations. But I don't think anyone believes that the kind of data sets that we're trying to handle with deep learning methods are multivariate Gaussian. And that makes it challenging to even study things, right? So it would be nice to have more realistic data generating processes. And one way to do that is with generative models, right? It's kind of a natural thing to provide even like a testing ground for different machine learning methods. And that has been done actually quite recently. People have suggested that as a way of basically generating data sets like CFAR10, but with a generative model. So I'm happy to send that paper to people who are interested in it. I don't think they used a GAN specifically in that case, but the idea is there, right? So that allows you to take as many samples as you want, basically, and then you can remove that problem of trying to estimate the covariance matrix, right? You can be undersampled when you're testing out your method, but when you really want to know the properties of these distributions, you can estimate them without any trouble. So it's a good idea, yeah, and people are working on things like that.
When you talked about this, relation between the overlap coefficients and this eigenvalue changes that we wanted to see and capture from variation from test and training distribution, and when you refer that as a robustness to covariance shift, what does developers do after, okay, you see this thing, and what does it mean in terms of me to make changes to my test set or training set?
Good question. So I think this is getting back to what I mentioned a few minutes ago of how can you use these results practically. And I think the main thing is giving some support for this idea that the way that you can really improve robustness is basically to focus on in-distribution accuracy. Like the best model that you can make for the original problem will also be the best model for the out-of-distribution tasks. Now, that's not always true. There are obviously examples to that you can cook up where it's not the case, but it's a good rule of thumb. So that's one practical recommendation. These kind of more specific things about measuring eigenvalues in your training and test distributions is much harder because of this. You have to estimate that, and to estimate that for high dimensional data, you need a lot of samples. So I don't know yet how to like operationalize that part of the theory. And I think it's like a very interesting question. But I don't have any good ideas yet. So, you know, hopefully someone else will have something. But.
Great. Let's see if we have any more questions.
Dr. Adlam, I have a question for you.
Great.
So when we have these many hyperparameters or tunable parameters, how does hyperparameter tuning actually fit into this this problem of solving this covariate shift, right?
Yeah, good question. Yeah. So there are hyperparameters in this model too. So let me just go back to that quickly. Yeah, so the hyperparameters are things like, you know, I could change the scale that my weights are initialized from, or I could use a completely different distribution. The really important ones are things like the activation function, you know, so changes in the activation function here result in quite different behavior. Similarly, the number of random features is a hyperparameter, and this is actually where these kind of analyses can be useful, right? So relative to training a neural network, doing the numerical procedure to calculate predictions for the test error is relatively cheap. So you could imagine like choosing hyperparameters for your neural network based on these theoretical calculations. And people haven't done it for exactly this paper, but there are other theoretical calculations about neural networks that are used in hyperparameter tuning. And yeah, that's something that works well already. Yeah, I mean, obviously, we're not trying to do something that is like set these hyperparameters optimally based on this task. Now, the reason for that is that this task is trivial, right? So we're trying to learn a linear function. So using nonlinear random features is not a good way to do that. Okay. The best thing you can do in terms of the hyperparameters is linear regression. So the reason that we're not doing that is we're deliberately setting up this mismatch between the model class that we're learning with and the true data distribution, because this mismatch creates some of the phenomena that we're trying to study. So it's a little bit different than you would traditionally think about hyperparameter tuning, basically.
Ben, how would you think the extension of this work, you know, in terms of, you talked about one sufficient condition that, you formulated, and how do you see, in terms of extending this work in understanding covariant shift, especially you talked about the dependence on random seed, and so I'm just,
yeah.
Any final thoughts, maybe with this question we can conclude, yeah.
Yeah, okay, so I have done other work that wasn't under covariate shift. It was just IID test data, where you look at a finer decomposition of the test error. So rather than just bias and variance, you also decompose variance. And with that decomposition, but basically the way the variance is decomposed is more or less like ANOVA. That's really the answer here. But you can also think about it as a generalization of the law of total variance. But what it allows you to do is say, I have this component of the test error, like how much of that is due to the randomness in the features? How much of it is due to the randomness in the data or the label noise, right? And those effects can be exaggerated under covariate shift too. We haven't published anything on that, but we've kind of looked at some of the calculations there. So you could imagine looking at that for a real problem and seeing like, oh, I'm actually seeing a lot of variance, a lot of my test error coming from the random seed in the training, basically. So what does that suggest? It kind of suggests that you should ensemble in a particular way, or you should regularize targeting that variance. And again, this is like kind of a difficult problem to connect to real neural networks practically, but I think it can be useful. So it can be interesting to see that, like, oh, there's this particular weakness in my training process that's causing a lot of error. Like now I'm going to target my interventions towards that. And the kind of simplest way to do that is with different forms of ensembling that we talk about in that paper. So yeah, there's definitely some connection there, but I would recommend like reading that paper in more detail if you're really interested.
Super. In the interest of time, we're going to conclude this webinar right now. And thank you, Ben, for your time and effort in preparing this thing. It's very insightful and useful. And we're going to make this recording, made it available online. So you will have access to the link as well for you to send it to others as well. So again, thank you so much. We'll look forward to collaborating with you, maybe in some proposals or papers as we work on. Thank you so much.
Yeah. Okay. Have a good day. Appreciate it.
Thank you.